Hi, this is Dr. Tyagarajan, Professor of Department of Electronics and Communication Engineering and Dean Academic of RMD Engineering College. In this video, I am going to explain the Flint's classification of processor organization. The processor organization deals with how the parts such as control units and processing elements of the processor are linked together to improve the performance of the processor. The processor organization is classified into four types. The first one is SISD, that is single instruction stream with single data stream. The second one is SIMD, that is single instruction stream with multiple data stream. The third one is MISD, that is multiple instruction stream with single data stream. The fourth one is MIMD, that is multiple instruction stream with multiple data stream. The processor organization is classified based on the number of control units and the number of processing units, that is ALU. But this processing unit may have more than one functional unit. Functional unit means, for example, addition, multiplication, then loading the data from the memory and storing the result in the memory. So for this you need different functional units. So this processing unit will have many functional units. So in the case of SISD, single instruction, you will have only single control unit. Then a single data stream, that means you have to handle a single data stream. For that you need only one processing unit. So a single instruction is fetched from the memory by the control unit and it is executed with the data fetched from the main memory. So a single instruction is fetched from the main memory and a single data stream is applied on this instruction. For example, the data may be obtained by the main memory to this processing unit, or the result may be stored in the main memory. So this is a two-way connection. So the data stream is having a two-way connection, but the instruction stream is having only one-way connection because the processed data will not be transferred to the control unit. Similarly, the instructions will be fetched from the main memory and it will be controlled by the control unit. So here in SISD, the instruction stream is single, that is one, and data stream is also one, that is you will have only one connection between the processing unit and the main memory. The next class is single instruction, multiple data. Since we are executing only single instruction, we have only single control unit, but we have to handle multiple data, so we have multiple processing elements. This type of arrangement will help you to handle arrays. For example, if you want to add n number of arrays, then each array is considered as a data stream and it will be stored in the main memory. So this is one array, this is another array, this is the nth array. Now the first element of the first array will be taken and it will be brought to this processing element. Similarly, the first element of the second array will be brought here, like that. All the first elements will be handled by each processing element. So all the first elements will be added. Now the second element from each array will be brought and that will be added. So each array is providing a data stream and each one will be handled separately by a separate processing element. So in this case, the addition is only one instruction. So single instruction is operated on multiple data streams. So it is more useful when you want to handle arrays in for loops. In this case, the processor should complete the current instruction, for example addition. It should complete it before it takes the next instruction. So in this class, a single control unit is controlling multiple processing elements. The next classification is multiple instructions with single data stream. Since we have multiple instructions, we have to use multiple control units, and each control unit is controlling its own processing unit, but a single data is passing through all the processing elements. So only one data stream is passing through all the elements, but many instructions are brought from the main memory to the control unit. The next classification is multiple instructions with multiple data streams. Since multiple instructions are to be executed, we have to use multiple control units like this, and multiple data streams are to be handled, so we are also using multiple processing elements. So each control unit is controlling its own processing element, and the data is streamed for each processing unit. So each process works on its own instruction and own data. Here the task executed by different processes are asynchronous. That is, each task, each instruction can start at any time and it can finish at a different time. This organization is actually representing a real parallel computer. Now let us see SIMD in detail. SIMD is a vector architecture and it is used for data level parallelism. In vector architecture, data are collected from the memory and they will be stored in a proper order in vector registers. These registers are operated sequentially using pipelined execution units. The results are written back to the memory. For example, you take this one. This is a single lane or pipeline with addition operation. So this is called as single add pipeline. So here this is one vector, A is one vector and B is another vector. The elements in vector A are stored in a set of vector registers and element B is stored in another set of vector registers. Now these two vectors are to be added, that is A plus B, and the result should be stored in C. So it can be represented like this, that is C is equal to A plus B, and A1 is the first element in the array, B1 is the first element in the array B, A2 is the second element in array A, and B2 is the second element in array B. Now the A1 and B1 are passed through the LAN to this functional unit, add unit, and both will be added and it will be stored in C1. Next, in the next clock cycle, A2 and B2 will be added and the result will be stored in C2. So, for each clock cycle, that is one addition is performed. So, through this pipeline, the elements of the array are passed. So, in this case, for each clock cycle, one addition is performed. Now, you see this second figure. Here, we have 4 pipelines, add pipelines, or we have 4 add lines. In this case, the elements in the vector are interleaved across these lines. That means every 4th element in the array or in the vector will be put here. For example, the 4th element is A4, A4 is put here, then B4 is put here. After that, the next elements will be A5 and B5, that will be placed in the next pipeline or lane. Then A6 and B6 will be in the 3rd line, then A7 and B7 will be in the 4th line. After that, A8 will go to the 1st line. So, like that, the data stored in the register, vector registers, are interleaved or distributed across these 4 LANs. Now, in this case, for each clock cycle, all the 4 elements are performed, that is added. Then in the next clock cycle, these are added. The second row provided here will be added. So, in this case, the number of clock cycles required will be reduced by a factor of 4. Now, you see this third figure. It is an expanded version with more functional units. Here we are using only one functional unit. That is, addition is the one function, but we are using 4 such units with 4 lanes. Similarly, here we have 4 lanes, lane 1, 2, 3, and this is 4 lanes are there, and we have 4 functional units in each lane. That is FP add, floating point addition, that is one functional unit. Then FP multiply, that is another functional unit, and the third and fourth functional units are here. That is for loading the data from the memory into the vector register and storing the results of the vector register into the memory. So, to operate load and store functions, we are using this unit. So, like that, we are having 4 lanes with 4 functional units. So, each LAN is using a portion of the vector register as we did here. That is, the first LAN is using the first element, then this one, it starts with 0, so this will be 1, 2, 3. After that, 4 will be operated by this lane, that is 4, then 5 is by this lane, and 6 is handled by this lane, 7, then again 8 will be handled by this lane. It is helping us to implement data parallelism. So the same data is executed in parallel. Here in parallel, here also in parallel, and here also the two arrays are executed in parallel. So it implements or it helps to implement data level parallelism. If you use old array processors for performing 64 additions simultaneously, you need 64 ALUs. But if you use SIMD vector architecture, then even with one ALU, you can perform 64 additions by passing the data through lanes and pipelines. So this reduces the hardware cost. In MIPS vector architecture, there are 32 vector registers and each register will point 64 vector elements, each of 64 bit size. That is, the elements, that is data in the vector will be of size 64 bits. So like that you will have 64 elements in each vector, and each vector starting address is provided by the vector register. The hardware get the addresses of the vector from these vector registers. This type of indexed accesses are called as gather scatter. The data need not be contiguous in main memory because indexed load instruction gather data from the main memory and put them in contiguous vector elements. Similarly, the results available in the vector register will be stored in the main memory in a scattered manner. It need not be contiguous. So the number of elements in a vector operation is not in the instruction or opcode. It is in a separate register. MIPS vector instructions are obtained by appending letter V to MIPS instructions. For example, add V.D indicates that it is addition operation. It is using two vectors and the size of each element in the vector is a double precision value. Each element is having 64 bit size. That means it is a double precision data. So add V.D will add two vectors and store the results in another vector. You see this instruction, add vector scalar dot D. So V indicates that there is a vector and S indicates that there is a scalar. So how do you add vector and scalar? The scalar value will be added with each element in the vector. Similarly, you see this one, load vector. So the vector available in the memory will be loaded into the vector registers, and store vector will store the results available in the vector register into the main memory. So these instructions will help you to write a program which will use vector data. Now let us see how to write an MIPS program using SIMD vector architecture. You see this problem, that is y is equal to a into x plus y. Here x is a vector and y is also vector, the vector x is to be multiplied by a scalar a and the result should be added with vector y and the final result should be stored in vector y. You assume that the vector x is pointed by the register S0 and vector y is addressed by the register S1. So how to write the program for this? Load the scalar available in the memory into register F0. To access the scalar value from the memory, you use the SP register. So this will indicate the address of the scalar. A within brackets $SP will provide the address of the scalar. From that, the scalar value will be taken and it will be loaded into F0. Actually, here you have to specify that the scalar is a double precision value. So you have to put L dot D. This D indicates that the scalar is a double precision value. Then you have to load the vector in the register V1. So for that you use this instruction, load vector. You observe that there is no D, that all the vector elements are double precision values. So you need not put dot D here. So this instruction indicates that you have to bring the vector from the memory using the register S0 because S0 is pointing the starting address of the vector, right? That vector is to be loaded into vector register V1. Then you multiply this vector by the scalar. The scalar is available in F0 now, vector is available in V1. Multiply these two. For that you have to use instruction MULVS, multiply vector scalar dot double precision. So in this case, V1 is the vector, F0 is the scalar. So this scalar will be multiplied with each element in the vector and the result will be stored in another vector register V2. Right? Now this A into X is over, that result is available in V2. Now Y is available in the memory. You bring that Y vector into a vector register V3. So for that again you use load vector V3 register, comma 0, comma S1. Because S1 is pointing, you see in the problem itself it is given, Y is pointed by the register S1. So you put 0 S1 here. So from this location in the main memory, the vector will be brought and stored in V3. Now you have to add this V3. V3 is Y. You have to add this V3 with this V2. So add vector dot D $V4, $V2, $V3. So V2, V3, you are having the results already obtained, right? V2 is having A into X, V3 is having Y. So both will be added, that is A into X plus Y, and the result will be stored in V4. Actually, the result is available in V4, that should be again stored in memory. So to store that value in the memory, you use SV, store vector. That is the store vector V4 into the memory location where that Y is available. Y is to be stored in S1. The location is pointed by the register S1. So store vector $V4 will store the result in the memory. So you again observe that SV is not using dot D because SV itself indicates that it is a vector operation, so it is a double precision number or double precision vector. So the result will be stored in the main memory pointed by the register S1.